Okay, the session is now recording. Good morning, colleagues. Good morning, Ms. Smith. Please note that this session is being recorded as I've indicated, and welcome to the Research Capacity Development Unit. My name is Lawrence, and I am delighted to be your moderator for today's session. I'd like to start off by thanking all the attendees for taking the time to join us, and most importantly, we'd like to thank our presenter, Ms. Smith, for preparing and giving this presentation. Before introducing Ms. Smith to you, I'd like to go over a few housekeeping rules. If you do have any question during this session, please kindly raise your virtual hands. And if you do not wish to speak, please kindly type your question in the chat box, and I will indicate it to the presenter to address the question. And as I've indicated that the session is being recorded and the presentation slides will be requested from our presenter and will be posted on our model communities. I will be posting a feedback survey in the chat session. Would please request for all you to fill it in so that we may gain insight on how we may improve, and also we use this feedback survey for our reporting purposes, as well as to provide some kind words to our facilitator for her hard work. So please allow me to read over Ms. Elizabeth Smith's bio. Ms. Smith's research interest focuses on applied statistics, missing data analysis, and data fusion. Prior to working in academia, she worked in social and market research as a data analyst and statistician using a variety of univariate and multivariate techniques to solve real-world problems. So without any further ado, I'd like to hand over to Ms. Smith. You may now begin the session. Thank you so much.
Thank you very much, Lawrence, and welcome everybody. Before I start, I think, well, you've seen my picture. I'm just going to put the camera on. That's what I look like now. As you can see, dressed nice and warmly for winter. I'm not going to keep the camera on the whole time, just to introduce myself and welcome to everybody. So I'll switch this off and share the screen so that we can start the presentation. Okay. Just get this in presentation mode. I'd like to minimize this. Okay, so the presentation today, statistical analysis, probability and distributions. Now, I think many of you will probably find that this doesn't feed directly into the research you are trying to do as a postgraduate student and what you're going to do, but it forms the basis of it. And as much as possible, I will try to relate this back to what we actually do when we do research. Now, just one of the things I cannot see if your hand is raised, so Lawrence will stop me if there are some questions. If you want me to clarify anything, please just raise your hand, ask your questions, and I'm happy to address the questions. And then we can also deal with more questions at the end of the session. Right, so without any further ado, this is the content, what I'm going to be talking about. First of all, just looking at probability analysis, what it is, some notation and terminology. We cannot get away from that part. I'll also then discuss the different kinds of probability, how probabilities can be represented, the various rules of probabilities, and then I've got a few examples where I will just show you how this is applied. Then we move on to probability distributions, which forms the basis of inferential statistics. To introduce that, we'll look at the language of statistics and data, define what a probability distribution is, and look at some common statistical distributions and how we calculate probabilities from these distributions. The last part before the application that I want to talk about in terms of probability distribution is how we fit distribution. And this is, I'm not going to go into a lot of detail with that particular one that fits better in terms of the inferential statistics, but I did want to introduce it here to show the value more of the value of probability distributions in statistical analysis. And then again, I will do some application with some common statistical distributions. So in terms of probability analysis, what exactly is it? Well, probability, it is a fundamental concept in statistics. We use it to measure the likelihood of events occurring, and it's all based on the number of possible outcomes out of the total number of outcomes that I could possibly observe. It plays a really important role in decision making. Probability provides this foundation for statistical inference. It allows us to draw meaningful conclusions about populations based on sample data. It helps us to quantify uncertainty and then make predictions, especially when we're dealing with random events. And it enables us to assess how good our estimates are in the face of uncertainty. We can talk a little bit more about that as we go along. So notation and terminology, just so that you understand the different concepts. I'm sure a lot of you have actually done some or other statistics course somewhere in your background. So this may just be part of the revision, if you like. But first of all, what is a probability? Probability is a numerical measure. It is a value between 0 and 1, ranges from 0 and 1. It cannot exceed those bounds, where a value of 0 means that the event is impossible. And a value of a probability equal to 1 means that the event is certain to happen. And of course, the closer the probability to 1, the more likely the event to occur. A random experiment is a procedure that results in an uncertain outcome. For example, if I roll a fair six-sided die, I am aware what can happen. I know exactly what can happen, but I do not know what will happen because my outcome, if I roll the die right now, is uncertain. Even if I go and I interview a random sample of people, I know the possible questions, what they could answer, but I don't know what they will answer. So that all falls under what we call a random experiment. The sample space is the set of all possible outcomes of a random experiment. In statistical terms, in notation, we denote that by the capital letter S, and the probability of the sample space, which is denoted as follows. So we always write probabilities in this way. Let's see, where's my pen? So P for probability of the sample space or whatever event is equal to 1. In other words, it is sure to occur. For example, if I flip a coin right now, I know it can land on either heads or tails, but the entire sample space, heads or tails, it will happen. It's either going to land on heads or tails with certainty. Therefore, the probability of my sample space is always equal to 1. An event is a subset or a portion of the sample space. So if I have an event called A, then I will denote the probability that event A occurs with P of A. An event that has absolutely no chance of occurring, in other words, the probability of that happening is 0, is called the impossible event, whereas the event that is sure to occur with probability 1 is the certain event. So probability of, for example, an impossible event, let me go back to simple examples. If I have a six-sided die with numbers 1 up to 6 and I roll the die, the die cannot land on the number 7 because there isn't a number 7. It is impossible for that to occur. And another example of a certain event, apart from the sample space that we've seen, the sun will come up tomorrow. Even if it is cloudy, with certainty we know the sun will come up tomorrow. The empty set is a set that does not contain any of the outcomes of the sample space, and the probability of the empty set is 0, therefore it is an impossible event. Some more notation and terminology. The complement of an event is the set of all outcomes in the sample space, excluding the event itself. And intersection of event refers to where events occur together. So the intersection of two events A and B, we denote this with A, and then like a cookie cutter, that's the intersection notation. A intersection B, it describes all the outcomes that are common to both A and B. In other words, both events must occur at the same time. Whereas the union of events just refers to the combination of events. So the union of two events, A and B, is denoted with A union B. I always explain to my students, it's almost like a coffee cup. I will unite the coffee and the sugar and the milk and the water and the milk all in the cup. I unite them all, and then I have the union and I have a cup of coffee. So it contains all the outcomes of event A or the outcomes of event B or both. Either A or B or both events occur. Mutually exclusive events. Two events are mutually exclusive if the occurrence of the one event means that the other event cannot occur at the same time. For example, I cannot give an online lecture and be physically face-to-face in class at the same time. Those two events are mutually exclusive. That means that the intersection of mutually exclusive events yields the empty set. Therefore, the probability of that event occurring is equal to 0. Exhaustive events refer to events that fill up the sample space. So if I have a set of events and I unite them all, take the union of all those events, if they fill up the sample space, the events are exhaustive. The last bit of notation here is a partitioning. Events that are both mutually exclusive and exhaustive form a partitioning of the sample space. You can almost think of it as a jigsaw puzzle. So a jigsaw puzzle, say a 100-piece puzzle, has 100 individual pieces. They do not overlap. They sit together nicely. And if I don't lose one of the pieces, and they fill up the entire sample space, in other words, I make my whole puzzle. And that means it's a partitioning of my sample space. Now let's talk a little bit about the different types of probability. There are two types of probability that I will mention. The one is called objective probability and the other is the subjective probability. The objective probability is calculated from experiments with a priori knowledge or through empirical observation, and it's all calculated in the same way. If I have an event A, then the probability of that event occurring is literally where I just count how many outcomes in my sample space sits inside this event A, and I divide that with my total number of outcomes in my sample space. So it's just a fraction of how many outcomes in event A divided by my total number of outcomes in the sample space, and that is the probability that event A will occur. I've got an example here. My experiment consists of a single roll of a fair six-sided die. In other words, each of the 6 outcomes are equally likely. Then I can work out the probability of observing an even number. That would be outcome number value 2, 4, and 6. So it's 3 possibilities out of 6, and that would be 50%. Or if I have a survey, let's say we ask grade 12 learners whether they would like to come and study at UJ or not. Please note that this number that I've put down here, the 17%, is not taken from anything published. That's just a number that I got out of my thumb. So don't quote that at all anywhere, please. So for example, the survey may say that 17%, say whatever the count is out of the total number of grade 12 learners surveyed, it translates into 17% wants to study at UJ. To further understand objective probabilities, I'd like to classify them in terms of 3 different types: marginal, joint, or conditional. A marginal probability is the probability of a single event A occurring, whatever that event is. Whereas a joint probability is where I have 2 events, A and event B, and how they coexist either through a union or an intersection. And then lastly, a conditional probability is the probability of a single event, say event A, given that event B has already occurred. And that would be part of the notation and calculations we will look at a little bit later. So a subjective probability, well, those probabilities differ from person to person. They're based on people's experience, their own opinions, their judgments. We only use subjective probabilities in situations where objective probabilities cannot be determined through observation, for example. An example of this would be, I may ask a person, do you think the traffic lights at the Kingsway Road and University Road will be working today or not? Well, people working at Doringfontein that never passed that intersection will never know this. They could make a judgment on it, but they won't be able to really say what their gut feeling is about what that would actually happen in that situation. In statistical analysis, most of the probability calculation is based on objective probabilities. That doesn't mean that there's no place for subjective probabilities. In some techniques, a starting point may be a person's experience or their expert knowledge or insight or their opinions that can be incorporated in the modeling. Mainly, we're going to work with objective probabilities, and these can be represented in many different formats depending on the nature of the probability. And the different formats could be notation, Venn diagrams, contingency tables, or tree diagrams. So looking at notations, probabilities are represented through the use of notation is very useful when the given probability information can be easily substituted into specific probability rule formulae. Then it's very easy to calculate this. Now, many of us have seen a Venn diagram. So Venn diagrams are very nice to visually represent how events coexist within the sample space. So the sample space is represented by a rectangular box, and then my events are represented by circles. We don't have to make the circles proportional to the size of the probabilities, but in this particular example that I have here, we can see that within the sample space there are 3 events, A, B, and C. A and B overlap, so they are not mutually exclusive, and C could be defined as everything outside of the union of those two. So it's a really nice way for us to visually see how events coexist within the sample space. A contingency table is used to represent probabilities or empirical counts in another word for this is a crosstab or cross-tabulation, where we have the results from one variable in the rows and the results from another in a column, or events in rows and columns, and they cross one another. They intersect, and it's very useful to represent counts or probabilities in the columns and rows of a table. A tree diagram is another visual representation. This can be used for many different scenarios. I prefer to use this specifically when we have conditional information. So if I've got an experiment that consists of several stages, my first stage is it's all represented as branches of a tree. And within a branch, I've got further splits into further branches. And within those further splits, I could split even further, making a tree diagram. So if you have conditional information, typically this is how it would look. You'll start with your unconditional information as the first split. And the next level, within every branch, it is split again. And what we end up with, so the notation we'll have here, I'll talk more about the notation a little bit, is that in my example here, where I have 2 events, A with its complement, and within each one of those, B with its complement, so conditional on it, it results in 4 branches. And through probability rules, the combination of each one of these 4 branches yield the 4 intersections that all make up the entire sample space. What is important if you work with a tree diagram is that at every level, we have, and my unconditional or marginal, the sum of the events must all add up to 1, just within this part here. And when I look conditional within each subset, each branch, the sum of all the probabilities must add up to 1. So it doesn't matter how many splits I have or how many branches I have. Within each subset, the sum is equal to 1. When I then look at all the intersections and I add all those probabilities together, the sum will again be equal to 1. And that's a tree diagram. All right. Now we look at the probability rules. So probability concepts are expressed in mathematical terms as a set of probability rules. What's underpinning all of these rules are 2 very important properties of probabilities. Number 1, a probability is a value that is bounded by 0 and 1. So it's a number between 0 and 1 inclusive. And the second property or axiom of probability is that if I take all the probabilities of all the events in my sample space and I'll add them together, I will get the sum of the sample space, or the value of the probability of the sample space. So I add it together, it's equal to 1. All of these rules are based on that premise. The first rule is the complement rule. The complement of an event implies that that event does not occur. In other words, it includes all the outcomes in the sample space that do not belong to the event. There are different ways to denote this. You'll see some textbooks will say A with a line on top, that's a complement, or A with a, A with a little C superscript, that's also a complement. Other places use A with an accent. So there are different ways to denote the complement of an event. And to visually illustrate it, what does it mean? If I've got event A in this Venn diagram, everything in my sample space outside of A, everything except event A, even if it covers part of event B, that is a complement. And the complement, so the complement rule is literally the probability of the complement of an event. You will agree with me when you look at this entire sample space. We know the sample space, the probability of the sample space is 1. So if I take the sample space, event A, just this circle of A, plus everything outside of it, I will get the total of 1. Therefore, I can calculate the probability of the complement of an event as simply the sample space probability minus the probability of the event, and consequently, the probability of A can also be written as 1 minus the probability of a complement. The addition rule is a rule that allows us to calculate the union of two events by looking at marginal probabilities as well as the intersection probabilities. If I've got my two events A and B, in this case they overlap, the addition rule says take the entire probability of A, add it to the probability of B, but then subtract the intersection probability. So if I take all of A and I add all of B, what we see is that this little bit over here, this intersection, the part that overlaps, is added twice, double counted. So we're going to remove them. So that is where the addition rule comes from. Maybe something I can add over here. If I've got mutually exclusive events and I've got event A and event B, there's no overlap because they are mutually exclusive, then my addition rule reduces to simply the probability of the union of those two events as just the probability of the one plus the probability of the other, because we know that the intersection probability of mutually exclusive events is equal to 0. Next one to look at is statistical independence. Two events are independent if the occurrence of one does not change the probability of the other occurring. We can then calculate the probability of both events occurring at the same time by simply multiplying the marginal probabilities. Best understood with an example. Let's say I play a game where I first flip a coin and then roll a die, whether fair or not. We know that the outcome on the die, whatever my outcome on the coin is, that's not going to influence the result on the die. Even if I flip the coin 10 times, every time I flip it, it is independent. The result will be independent of anything else that has happened. But I can work out the probability of observing tails on the coin and a 2 on the die. So there is an intersection. And to find that intersection, all we have to do in terms of our rule is take the probability of the one event multiplied by the probability of the other event. And the key word here, the fact that the two events are independent of one another. Right, conditional probability. Conditional probability, if the occurrence of one event affects the occurrence of a second event, the events are dependent. And for two events A and B, if event B has occurred, what effectively happens is that the sample space is reduced to event B. Then the probability of another event A, given that B has happened, the notation for that is with this vertical line. So it's the probability of one event with my vertical line, and after the vertical line, I have, this is my conditioning event. To work this out, we use notation where we look at the intersection of the two events and we divide it by the marginal probability of the conditioning event. I would like to illustrate it here as well. What effectively happens, I think was there a question? Oh. No, I think, no. It's just there's somebody in the lobby. Okay, Lawrence.
Yes,
okay.
I know. All right.
Thank you.
You can proceed.
No problem.
Thank you.
All right, so to illustrate what this happens, effectively what happens with conditioning, I know that my students that I teach, conditional probability is usually a bit of a foreign concept. All that happens here is that my sample space is reduced to another event, the one that I condition on. So visually, this is what happens. At the moment, in this picture, this Venn diagram denotes my sample space, and I've got two events occurring and they overlap, or could occur within that sample space and they overlap. If I now say for certainty that event B has occurred, effectively what happens is you take your pair of scissors and you cut away everything except event B. So B becomes my brand new sample space. And then I have that little bit of overlap with A. And what I then work out is this portion of event A relative to event B, because I know B has occurred. To give you an example of this is, I'll again use a student example. Let's say I record information where I have students, whether you attend class or not. So let's say event A is attend class, and complement of A is don't attend class. Event B is pass the course, and its complement is fail the course. So if I say amongst my students who pass the course, so only within event B, what proportion attended class? That means I am conditioning on attending class, event B. So amongst that subset, I'm not interested in the students that don't pass the course. In this particular question, I only want to look at that portion who pass, given that they have attended class. Now, what is important to note here is that when I condition, I will write this out. Let's say I want to now look at the other conditioning, the event of probability of event B, given that A occurred. In terms of notation, that is the probability of the intersection B and A divided by the probability of the conditioning event. And when you look at the numerator with both of these, the intersection of A with B is exactly the same as the intersection of B with A. So my numerator is exactly the same. What is different is my denominator, because I'm conditioning on a different event. It looks very different. In that particular case, I know that event A has occurred. I'm still looking at the portion where there's an intersection, but now I'm looking at it out of a different subset. So my new sample space is a very different subset. And that is what conditioning is all about. Right. Now, related to conditioning, if I take this equation and I just do a little bit of algebra with it by multiplying out the denominator, I get an expression for my intersection in terms of a marginal and a conditional probability, where the marginal probability and the conditioning event is the same. Now, if you look at both of these equations, the one that's typed and one I wrote down, I basically get the same thing, isn't it? Whether it is A times the conditional probability B given A, or the probability of B times the conditional probability of A given B, both of them can be used to calculate the probability of an intersection. And it all depends on what information I have available. So I showed the first one, and it can also be expressed as probability of B multiplied by A given B. And note again, my conditioning event and marginal event are the same. All right, so that's how we can find intersection probability if we have conditional and marginal information available. So it depends on what we have, and we can just calculate the intersection probability. Okay. Takes me to the law of total probability. Now, if you look at this formula, forget about the sum for the moment. Just look at this formula. It looks very much like one of these, isn't it? So I have a marginal probability multiplied by a conditional probability, and my marginal conditional events are the same. So the marginal and conditional events are the same. So effectively what I have is that this entire product is just the intersection between events A and events BI. And what we have here with the law of total probability is that we can, depending on what information we have available, we can find the probability of an event by just looking at all the different intersections. And those intersections can be calculated from conditional and marginal information. So let me read through this just to put it more in context. So the law of total probability, it's a useful tool for computing probabilities, specifically in situations where it's so difficult to just find this overall probability of A directly, but it's easy to find the conditional probabilities. If we look at this Venn diagram, I'm interested in calculating the probability of A, and you will agree with me that I can divide A into 4 little pieces. This little intersection over here, another intersection over here, a third intersection, and a fourth intersection. If I take those 4 pieces and add them together, put them together, I have my entire probability of event A. Each one of these intersections. So let me just make notation. So this is the intersection of event A with event B2. But from the multiplication rule, if we have conditional information available, we can write this, its probability, as the probability of an event multiplied by a marginal event multiplied by a conditional probability. And I can do that for each one of these 4 pieces of A. And if I add them together, just use the sum, what I get is the overall probability. And that is known as the law of total probability, which is used in something called Bayes' theorem. If you look at this expression in the denominator, that is exactly the law of total probability that I've just shown you. And in my numerator, that is just the intersection probability that I can calculate from the multiplication rule for a single event A and a single event Bj. What you note when you look at Bayes' formula is that the conditional information on the right-hand side of this equation compared to the conditional probability that I'm looking for on the left-hand side seems that the events have been swapped. I'm looking for the probability of event Bj given A, but the information I have available is the other way around. I condition on another event. This is where I condition not on A, but on event Bj. If that is the case, then we use Bayes' theorem. A bit of background with Bayes' theorem. It was developed in the 18th century by a Reverend Thomas Bayes. So he was a bit of a gambler, and he wanted to just calculate probabilities and see what will happen if I update my information, change information. So in light of new information, can I revise my probability calculation and calculate new posterior probabilities? So this theorem is a very special application of conditional probabilities, and it makes use of the law of total probabilities. And it can be seen as sort of an inverse problem, as I said, sort of swapped around. We are given an effect and we must calculate the cause, not the other way around. There is, in fact, a whole field of study in statistics that deal with Bayes' theorem. This is the basis of it, and it's called Bayesian analysis. It is a methodology to do inferential statistics and estimate parameters, where you start off with prior information and you observe new information and you keep updating your information to get the better estimate. So it's a whole field of study just based on this equation from Reverend Thomas Bayes. All right. Okay, well, that's the theory of probability analysis, and I will show you some calculations here, pen and paper calculations. And I know that some of you may say, but I'm not going to do this in my research. And the answer to that is probably you're right. But some of this, the ideas and the concepts behind it, even if you work with data collected and empirical data that you've observed and calculating relative frequencies from that empirical data, there will still be certain things that you might look at in terms of what is the marginal counts that I have, the conditional, the joint, and if that is used to estimate proportions in the population, then we are back with dealing with probability analysis. Okay. So let's look at the first one. I've got two events A and B defined on a sample space. Sample space in this case is denoted with omega, but we can also denote it with S. And I give you three different probabilities: the probability of event A, of event B, and the intersection of A and B. Now, because of what was given, fits nicely into my probability rules. So if you know your rules, you can see very easily, if I'm looking for the union of events based on what was given, I can just use my addition rule. So I can very easily calculate the probability of the union of these events as just the probability of the one event plus the probability of the other minus the probability of the intersection of these two events. So it's a simple matter of just substituting values into that equation. And the answer is 0.7. So that's for the first part. The second one, I've now shown you here a different notation. When I write it down, I will probably just use my normal one, looking for the probability of, sorry for scribbles, let me just erase that, A complement intersection B. In order to do this, I'm going to start somewhere else. I'm going to use the law of total probability. The event B is the portion where it overlaps with A plus the part where it doesn't have anything to do with event A. Just to show you again, this is event A, that's event B. The intersection of the two events plus this part where it intersects with a complement of A combined through the law of total probability gives me event B. This is an equation. I can do simple algebra. I'm looking for the probability of A complement intersection B. So I know the probability of B. I know the probability of the intersection. So again, using just my probability rules, I can calculate this very easily. This is 0.5 minus 0.1, and the answer is 0.4, just by using my rules. All right. In our next example, I want to show you how we use a contingency table. Two events, A and B, such that the probability of A is given, B is given, and the intersection is given. And we're going to construct a contingency table to represent all the probabilities in the sample space and calculate various probabilities around this. Now, in a contingency table, if I have event A, event B, and for both of those I have complements, we can set up our table like this. I've got event A with its complement, event B with its complement, and then I will have the totals in my columns and my rows. And I know that the entire sample space must add up to 1. At this point, we're going to play what I like to call the probability Sudoku, and we just put down the information that's given and fill in the blanks. We know that the overall probability of event A is given as 0.7. Overall probability of B is given as 0.4. And the intersection A with B, which is this overlap, the cross where A and B both occur, that is given as 0.2. We have now enough information to complete this entire table. We know the sample space must add up to 1. So if event A occurs with probability 0.7, then its complement will occur with probability 0.3. Similarly, for event B, its probability is 0.4, therefore the probability of B complement is 0.6. And we can literally just fill in the blanks because we know if I add the probability of A intersection B plus the probability of A complement intersection B together, I will get the whole of B. So 0.2 plus something must give me 0.4, therefore it must be 0.2. And we just fill in all the different cells of this contingency table. We can now calculate all the probabilities. To find the union of an event, we can use the addition rule, but we can also use just the logic of what is a union. A union is either the one event occurs or the other or both. And a very simple way in a contingency table to do this, I like to use tick marks. So everywhere I see event A is over here. Everywhere I see event B is over here. And when I look at my tick marks in the 4 cells, this corner one, nothing happened over here. So it's either only B occurs, or only A occurs, or both. So if I simply add those 3 probabilities together, I will get my probability of the union A with B, that is 0.2 plus 0.2 plus 0.5, and that is 0.9. Or we could have just said it is 1 minus 0.1. So it's just a complement of this bottom right corner of my contingency table. Right. Let's erase some of the things here. Looking at the 2 conditional probabilities, the probability of A given B. To calculate this probability, we can use our rules, which is the intersection divided by the marginal, and that's exactly what we're going to do. But from a logical, practical application perspective, a very simple way to do this in a contingency table is to say, what is my conditioning event? So I am interested only in where event B occurs. I am not interested in event B complement. So I temporarily eliminate that. I'm not going to delete it forever. It's just temporarily. My focus is event A. So it is the probability of event A occurring out of this new subset or new sample space, which is a total of 0.4. So that would be 0.2 divided by 0.4, which is exactly the intersection probability divided by the marginal. And this gives me the probability 0.5. Let me just eliminate that again so I don't lose it. Our next one is the probability of B given A, just to show you again that these are 2 different subsets. I am now conditioning on where event A occurred. So I am temporarily eliminating anything to do with event A complement. And I'm interested in seeing what's the probability of event B out of this new subset, which is 0.2 divided by 0.7, and that gives me an answer of 0.29. So clearly, what you should take away from this, again, is that depending on what I condition on, the conditioning probability of A given B is not the same as the probability of B given A, because I work with a different subset. Now, I just want to pause here for a little bit, because I've just been talking about probabilities and events, and that makes absolutely no sense from a practical perspective. But let's say that we've collected some information from a survey, and I asked males and females, do they drink Coca-Cola, yes or no? I could look at this contingency table as maybe event A being A versus complement could be male versus female, and event B could be drink Coca-Cola or not. And then I will count out of my sample how many males drink Coca-Cola, how many males do not drink Coca-Cola, how many females drink Coke, how many females do not drink Coca-Cola. And I'll have a total sample space, my N over here, and I can work out the relative frequencies of each one of those 4 intersection events occurring. And when you work it out, it may very well look like what I have shown you here, which is just in terms of probabilities. Now, why am I saying this? I'm saying this because when I observe information in a sample, we start off by describing that with just contingency tables and relative frequencies. But if I do inferential statistics, I'm going to use my sample information to estimate what is happening in the population. So if it turns out that in my sample, 20% of my sample are males who drink Coca-Cola, I could use that if I've got a big enough sample and I do inferential statistics. That could translate into the probability of that event occurring in the greater population context. So if you're a market researcher, or the Coca-Cola company for that matter, and you want to profile the consumers, then that becomes important information. Right. So our starting point in statistics is our probability, very theoretical mathematical concepts. When we go down to sample information, once we've calculated that, it can be returned back to the population context when we do inferential statistics. Just saying this so that you can understand that these things are not separate from one another. They are related to one another and also not redundant when we think about probabilities. All right, sorry, waffling on a little bit. Let's move on to a few other questions. So in terms of independence, it's really important when we have independent events that we take note of that. So if we've got a courier company with 2 delivery vehicles, and the probability that any vehicle is available at any given point in time is 0.85, excuse me. And let's assume for a moment that the availability of one vehicle is independent of the availability of the other. So an order is placed. What is the probability that only one of the 2 vehicles would be available? To calculate this, the key word is independence, which means if I denote, let AI be the event that vehicle number I is available, then I can work out the probability that only one of the vehicles is available. In terms of notation, this is the probability that the first vehicle is available and the second vehicle is not, or the situation where the first vehicle is not available and at the same time the second vehicle is available. And because of independence, we know that if 2 events are statistically independent, the probability of the intersection is simply the probability of the product of the respective marginal probabilities. Just because of knowing it, they are independent of one another, which is now pretty simple. The probability that the first vehicle is available is 0.85, and the probability that the second vehicle or the other vehicle is not available, well, then that's just 0.15. Probability of the first vehicle not available is 0.15, and the probability that the second vehicle is, because of independence, we can work this out. So the probability of this event occurring is 0.255. So if I work for this company or a manager at this company, I can look at that and say, okay, at any given point in time, there's only about a 26% chance that only one of my 2 vehicles will be available. And we can work out the availability of any of these scenarios, both of them, none of them, etc., just from knowing they are independent of one another. Right. Okay, let me just check my time. I'm going to do this next question quite quickly, just to show you in terms of the decision tree. We've got a manufacturing plant. There are 2 machines, A and B, that are used to manufacture a mechanical part. Machine A is used 60% of the time, and machine B is used 40% of the time. The probability that machine A produces a defective part is 0.1, while machine B has a 50% chance of producing a defective part. Construct a tree diagram to represent the probabilities. Now, without that instruction, if we just look at this specifically, we have 2 machines, A and B. 10% of the parts produced by machine A is known to be defective. Now, that's a conditional probability, because that probability given has got absolutely nothing to do with the parts produced at machine B or by machine B. This is all to do with the parts produced by machine A. So given that A is used, the probability of defective is 0.1. So for this, a tree diagram is very useful. So we have our 2 events to begin with, unconditional, machine A, machine B, and each one produces a part that's either defective or not, defective or not. The given probabilities, machine A is used 60% of the time, and machine B is used 40% of the time. And as you can see, it all adds up to 1. Amongst all the parts produced by machine A, 10% are defective. And if 10% are defective, that means 90% of the parts produced by machine A are good. Similarly, for machine B, there's a 15% chance of producing a defective item. So the defective items coming from the items coming from machine B, 15% are defective, therefore 85% are good. And we know from the multiplication principle, if I multiply marginal with a conditional probability, I will get my respective intersections. In this particular case, we have 0.06, so 0.6 times 0.1. 0.6 times 0.9 is 0.54. This is also turned out to be 0.6, and this is 0.34, if I'm not mistaken. And that's my tree. Okay, yes, I've got a screenshot of it on the next page. What is the probability that a randomly selected part was manufactured by machine A and it was good? And that means it's machine A and it was good, in other words, not defective. So I'm interested in this branch and the probability of that happening. So it's the probability of A and not defective. That is simply the product of those two respective probabilities, equal to 0.54. The proportion of parts that are defective. That means I need to look in this tree and find all the parts, all the branches where I have defective items. The probability that a part is defective comes from two parts, either, or two sections, if you like, two machines. Either machine A produced it and it's defective, or machine B produced it and it's defective. So it's just those two branches. Comes from the multiplication principle, so it's 0.06 plus 0.06, and 12% of all the parts produced by this factory is defective. Okay, that's from the law of total probability, which takes us to our next question, which is this. A randomly selected part is tested and found to be defective. What is the probability that it was produced by machine B? It usually helps when you write this in notation. I want to know what is the probability the part was produced by machine B, given that it is defective. If you look at the information, the conditional information provided in this branch, it is all conditioning on which machine it is. In this particular probability that I'm looking for, I'm conditioning on whether the part is defective, specifically that the part is defective. And if you remember what I said in the beginning, when I looked at Bayes analysis, it's almost that inverse problem, isn't it? I'm looking for the probability of B given defective, but the information that was given to me was the probability of defective given that it comes from B. So it seems swapped around. In other words, I need to use Bayes' formula. A very simple way to use Bayes' formula is to look at the conditioning event and just identify the branches that deal with that particular event, and that becomes the denominator. So it's going to be 0.06 plus 0.06 through the law of total probability. Then the specific event that I'm interested in, probability of B, all I need to do is find the branch dealing with event B, which is this one, and that intersection probability becomes the numerator. And what we've just done, which this is equal to 0.5, what we've just done is that freaky formula of Bayes' analysis. It is by reducing my entire sample space of all parts produced by this factory just to those parts who are defective. And amongst the defective parts, I can now see that 50% were produced by machine B, therefore the remaining 50% were produced by machine A. Okay. Right, so that covers probability analysis, and perhaps I'm going to stop sharing. Maybe at this point, I can ask if there are any questions.
Thank you so much, Ms. Smith. Really appreciate your presentation. Very insightful. At this stage, there isn't any questions from the participants. As I have indicated in the beginning, that if you do have any questions, please kindly raise your hand, or you can type your question in the chat box, and I will indicate to our facilitator.
Okay, yeah, it doesn't look okay. So if we don't have questions at this particular point, then I'm going to go back to sharing, and then we're going to look at probability distributions.
Yes, I think we can
I
do
think let's
that.
do that. All right,
Then at the
let's do
end,
that.
maybe we can just open open discussion at the end, probably.
All right, then.
All right, thanks.
Okay, just minimize this. Okay, probability distribution. So I'm going to start my whole discussion around probability distributions with the language of statistics. Some of this part, the next 2 pages, probably feeds more into inferential statistics, but it's still important because I'm going to talk about it. So the language of statistics and data. It's really important that we understand these different concepts when we work with doing any statistical analysis, when we do research and we collect information and we deal with populations and samples and all that. It's really important that we understand these concepts as well as our data and the nature of our data. So first of all, a population. A population is the entire collection of individuals, objects, or items under consideration, and we typically denote the total number of elements in the population with the capital N. A parameter is a constant value that is usually unknown that describes some measurable aspect of a population. Usually we denote population parameters with Greek letters. So you'll often see things like the Greek letter mu or sigma or pi or things like that. And that typically denotes population parameters. So a population parameter is a numerical summary measure that describes something about the population. It is fixed, but generally unknown because we don't generally know what's happening in the entire population. A sample is a subset of the population of interest. Now, we use samples to collect information because it's not always feasible or possible to consider the entire population. We will then collect a sample of size n, so lowercase n denotes the sample size. If we calculate numerical summary measures from our observed information in a sample, we call that a sample statistic. And generally, we denote sample statistics with Roman letters. We'll have a random variable. We'll talk about variables in a minute. And we say the variable is x, so x, little x, come on, right, nicely, with a line on top, that is x bar, and that would denote the average of a random variable. So what is a sampling unit? That is the object being measured, counted, or observed. So broadly speaking, statistics, you can see it in these 2 branches, descriptive statistics versus inferential statistics. Descriptive statistics refer to all the methods that are used to organize and describe information collected in a sample, whereas inferential statistics are all the methods that are used for making generalizations, predictions, or estimates about the behavior of the population based on all the information I've collected in my sample. We infer the population behavior using sample information, and that falls under inferential statistics. Right. A random variable is a characteristic of the elements of a population or sample, but in sample context, we then just call it a variable. So it's a characteristics of the elements of a population for which the observed values differ from element to element. So that's called a variable. If I measure people, take my tape measure and measure it, it's going to differ from person to person. It's unique to that individual, to that sampling unit. So my variable itself will be height, and it can take on different values depending on the group that I have looked at. We typically denote random variables with capital letters, just our Roman letters. Data is the collection of all variables measured. That combined gives me my data. Now, I want to go a little bit more in detail in terms of variable type, because that feeds into, so important to us, for us to understand what type of data we have, because that dictates what kind of analysis we can do. We've got 2 types of data, or types of variable, categorical or numerical. Categorical variables, it's also known as qualitative variables. Now, these variables allow for classification based on some characteristic. Okay, eye color, blue, brown, green, gray. So it's some or other characteristic. That's a categorical variable. A numerical variable, that's also known as quantitative variables. These are naturally measured as numbers. Numerical variables are further classified as either discrete or continuous. What we mean with a discrete random variable is that the variable can take on values by counting, and it consists of a finite number of values. It can also consist of an infinite number of values, but we say countably infinite. But that doesn't happen very often. Basically, a discrete random variable, if you can count the possible values of the variable on your fingers, so 1, 2, 3, 4, 5, including 0, there are no half numbers. We have a discrete random variable. Whereas a continuous random variable assumes values obtained by measuring and consists of an infinite number of values along the real line, such as the variable age. So I know a lot of us, we will say, whenever we talk about ages, unless you're a young child, we will round up or round down. If you get older, you start rounding down to age in completed years. But the reality is that every second we get older, age is a true continuous measure. We just don't measure it that way when we talk, but it is in fact a continuous random variable, not discrete. Now, the next page is just to understand the data a little bit more. It's our scale of measure. We've got nominal, ordinal, interval, ratio. The first two, nominal and ordinal, if I've got categorical data, that would either those variables are either measured on a nominal or ordinal scale, whereas numerical data measured on an interval or ratio scale. What's the difference? A nominal scale of measure is a categorical variable that consists of two or more categories with no intrinsic ordering. For example, person's eye color. There's no logical way in which these four categories can be ordered. We can maybe just order it alphabetically. Doesn't matter, right? Whereas an ordinal scale is also categorical. It also has two or more categories, but it can be ordered or ranked. For example, a person's age that are classified as a young, middle age, or old, even if I denote it with code 1 is young, code 2 is middle age, code 3 is old, that doesn't mean it's numerical, it's just a code. So these three possible values are ordered in a logical way. You start with young, you go middle age, and then you go old. There's not an arbitrary order to it. That's an ordinal scale. In terms of numerical variables, an interval scale, there are very few variables in the world that are measured on an interval scale. It's numerical. So the values can be arranged in order, but there's no true or absolute zero. In other words, the value of 0 is an arbitrary reference point. Differences between data values are meaningful, but ratios are not meaningful. Compare that to the ratio scale, which is also numerical. Values are ordered, but 0 is true or absolute. Differences again are meaningful and ratios are meaningful. So let me illustrate it with an example. So for an interval scale, if I say I measure temperature in degrees Celsius, it's numerical, but 0 is arbitrary. It does not imply the absence of the measure. So if there's 0 degrees Celsius outside, it doesn't mean there is no temperature. It means it's cold. It's an arbitrary reference point in terms of how the scale was developed. The ratios in an interval scale does not make sense. So if I say 40 degrees Celsius versus 20 degrees Celsius, we cannot say that 40 degrees Celsius is physically, it feels twice as hot as 20 degrees Celsius. We cannot quantify it in that particular way. Compare that to a ratio scale, where 0 means exactly what it says. If I measure the amount of money in my bank account and it says 0, that means I have no money. It means the absence of the measure, and that makes a ratio scale. In this particular case, ratios do make sense. So 40 Rand is definitely twice as much money as 20 Rand. And that's the key difference. It's about what 0 does. But there aren't many interval scale variables. There are few. Now, temperature measures, longitude measures, a lot of psychometric measures that are developed from a battery of questions are all measured on interval scale. But the majority of numerical variables are actually measured on the ratio scale. Right, now that done, let's get into what is a probability distribution. So a probability distribution is an assignment of probabilities to each distinct value of a discrete random variable or to intervals of values of a continuous random variable. Step back a little bit to probability analysis. We calculated individual probabilities. But if you then calculate all the probabilities around the entire sample space, you will see how those probabilities are distributed across my scale of measure. Right, or of all the possible outcomes, how it is distributed across the scale. That is a probability distribution. These probability distributions reflect distributions in the population context. They are constructed either from an experiment with the complete distribution known in advance, we call that a priori. That is like flipping a coin. If I've got a fair coin, then I know it's fair. It's a 50-50 chance it lands on heads or lands on tails. So if I code that as 0 and 1, then a priori, I know that the distribution of the possible outcomes of that experiment is land on heads, 0.5, land on tails, 0.5, a priori. Now, it can either be constructed in that way from an experiment where the complete distribution is known in advance, or from empirical data, which then feeds into inferential statistics, because we then use that as an estimate of the population distribution. Our population parameters for central tendency, variability, and any other parameters of a probability distribution exist, and we can calculate that. In terms of notation, the population mean, we said we denote the population parameters with Greek letters. So this mu, which is a U with a nice long tail, is called the expected value of my random variable X. So what do I expect to happen on average in the population? The population variance is typically denoted with my Greek letter sigma squared. So that is variance. And the population standard deviation, which is the square root of my variance, is just denoted with sigma. Probability distributions that we generally work with in statistics can be either discrete or continuous. Yes, of course, we can have probability distribution for categorical variables, but generally the probability distributions that we're going to touch on are just for numerical variables, either discrete or continuous. So a discrete probability distribution, it's referred to as the probability mass function of a random variable, of a discrete variable. It is where a probability is assigned to each distinct value of the random variable. The probability that that random variable is equal to a particular value is then denoted as follows. So we will say little p of x, or typically the probability that my variable is equal to a particular outcome. Think of this. I flip a coin twice. I count the number of times that that coin landed on tails. So out of 2 flips of a coin, either it doesn't happen, so the number of times it lands on tails is 0, or it only landed on tails the first time I flipped it, or the second time, but not both. So then the number of tails is 1, or both times it landed on tails. So the possible values of such a variable is 0, 1, and 2. And if I calculate the probability of each one of those 3 events occurring, I will have the probability mass function of my random variable x. In the continuous context, a continuous probability distribution, we refer to that as the probability density function. It is a smooth curve that is generated through a mathematical equation, and we can use that to model the shape of the distribution of our random variable. We will denote that with little f, lowercase f, of my random variable x. When we work with continuous random variables, we do not work, it's not our probabilities. We're never interested in the exact values. We are interested in the density around a point. An example I always use is if I can freeze time right now, and amongst the people in this session now, we can say, well, what's the probability of finding somebody that is exactly 25 years old, 6 months, 3 days, 2 hours, and 10 seconds? The chance of that precise numerical value of observing that, in reality, that chance of that is very small. But if I say, what's the probability that somebody is between 25 and 30? It's more an interval around a point. That is more realistic for continuous random variables. Okay. In statistical analysis, observed information consists of random error or variability, and it never conforms to a perfect distribution. So why are we using probability distributions? Well, in reality, a lot of variables can be naturally described to a certain shape. And populations are also dynamic. Think of this. If I freeze time right now and I was able to record the income of every single person in South Africa right now, or adult in South Africa, and I make a picture out of it, the picture may look like this. So we know it's a very skewed distribution. Okay. Now let's say a month later, I freeze time again and I go to every adult South African. Things have changed. In a month, things have changed. I'm never going to get the same picture, but it's going to be very similar. Even though populations are dynamic, the general trend of that random variable in the population context will stay the same. If a variable can be reasonably described using some of the known distributions, the beauty of that is that these known distributions have beautiful properties that we can then use to describe the shape of the distribution and population, the measure of central tendency, variability. We can calculate probabilities around that. So we actually can estimate quite a lot about the behavior of a random variable in the population context. Right, so it allows us to calculate probabilities, estimate parameters, and also then incorporate measures of certainty or confidence in our estimates. As statisticians, we are never 100% sure about anything. We are always sure enough, and we tell you how sure we are, 90% or 95% confidence. So we attach a measure of uncertainty or certainty for that matter to our estimates. Excuse me. As an example, just to illustrate this, let's look at these 4 random variables. The time spent waiting at a traffic light under normal conditions, in other words, not load shedding, not peak hour traffic, just normal conditions. The income distribution in South Africa, the height of the female population, and the lifetime of a light bulb. So if I look at these 4 distributions, they're all very different. Think about the time spent waiting at the traffic light. Well, that really depends on what time you end up at the traffic light, isn't it? So if it's already green by the time you get there, you don't spend any time there. But if it just turned red, you have to stop. And it lasts maybe, 2 minutes? So you have to wait 2 minutes. But if it's already turned red a minute ago, your waiting time is only 1 minute. So it all really depends on when you get there. So the time spent waiting at the traffic light under normal conditions is anything between 0 and 2 minutes. Any number with all equal probability. So this picture could reasonably describe this particular random variable. The income distribution in South Africa, well, we know, excuse me, that the income distribution in South Africa is very skewed. So the majority of working people earn on the lower end of the scale and only a handful of people on the upper end of the scale. So this picture, maybe even more skewed than this, is the best reflection of that distribution. Then think about the height of the female population. Let's say we'll only look at the adult female population. It's quite reasonable that the majority of adult females are approximately average height. And then you have only a few really short females and a few really tall females. So this picture over here will reasonably describe the height of the female population. Lifetime of a light bulb, because of decay, when you switch a light bulb on, it works beautifully. And then depending, it can go at any time, but the longer it lasts, the lifetime goes. So this could reasonably describe, and the decay is exponential, the decay of a light bulb. So what we're trying to achieve with probability distributions with random variables is to say, can I find a picture, a shape, a distribution that reasonably or best describe the behavior of this measurement in the population context? And if I can and fit it on top of that, then what we will have is actually quite a lot, because all of these distributions are such that the area under the curve is equal to 1. In other words, it covers the sample space. So I can work out any portion under this curve, and that directly translates into the probabilities of events occurring. So probability distributions are very important in the statistical context. Here I've got a short list of some common statistical distributions. I'm not going to go through all of them. I will illustrate a few of them. But some of the discrete ones, we've got Bernoulli, which is an experiment with only 2 possible outcomes. My binomial random variable counts the number of successes out of n trials, whereas the Poisson counts the number of events occurring in an interval. Our geometric distribution counts the number of trials until the first occurrence of an event. In other words, say I flip a coin, how many times must I flip it before it lands on tails for the first time? And the negative binomial is related to that, is where I count how many times must I do a trial until I observe the kth occurrence of an event. Back to the coin. How many times must I flip the coin until I count it landed on tails 10 times, for example? Those are all discrete distributions. Continuous distributions, a uniform distribution where each outcome within a defined range has an equal chance of occurring. There is also a discrete version of the uniform distribution. I didn't add it in the top, but there's also discrete uniform. My exponential random variable measures the waiting time until the first occurrence of event. Let me go back to the coin. No, let me do a customers. How long must I wait until the first customer walk into my shop? Whereas the gamma distribution measures the waiting time until the kth occurrence of an event. So I'm standing in the shop. How long must I wait until the 5th customer walks into my shop? Right. Now, the normal distribution, a lot of you probably most likely heard of this. It's a symmetrical and bell-shaped distribution, which is the most important distribution in statistics. And related to that is our student's T distribution, which is a generalization of the standard normal distribution, and it's used in inferential statistics. The chi-square distribution is also used in hypothesis testing, specifically if I have count data. So those are the common distributions, and I will look at 3 of these and how we calculate probabilities from these distributions. So for these distributions, all of them have been expressed in general form. So they will have an equation that will either create the individual probabilities in the mass function or an equation that creates the curve to create that density, probability density function, the picture. And then we can calculate probabilities around it. Our binomial random variable counts the number of successes out of n trials. It's discrete. It can take on any value from 0 up to n. And it's characterized by 2 parameters, the number of trials n and the probability of success, p. This distribution is given in general form. Notation-wise, typically we'll say a random variable x is binomial with parameters n and p. And then we have a formula where the probability that the variable takes on any one of the possible values, 0 to n, can be written as or calculated as n combination x. So that's actually n x with smaller brackets, not so big as this, which is just from combinatorics. It's counting the total number of subsets of size x that I can select out of n. My probability of success raised to the power x, my probability of a failure raised to the power n minus x. Right. Now, I know you're not going to do very much of these calculations, pen and paper. We'll do one very quickly in the exercise. And the expected value of such a distribution is I just multiply my 2 parameters n times p, and I say, well, that's what I expect will happen on average. Now, before we turn the page, a random variable is binomial, so only if the following 4 properties hold. Number 1, the experiment must consist of n identical trials. Cannot be flip a coin and then roll a die. It must be identical trials. Each trial consists of only 2 possible outcomes, a success or a failure. Now, something about this, a success doesn't necessarily have to be a positive thing. It's just the focus of what I'm counting. And if I'm counting the number of accident fatalities on a stretch of roads out of 10 accidents, that is a success, is the number of fatalities. Now, that doesn't sound very successful, That's just the focus of my count. So it's not a success as in something good. It's just what I'm counting. And the probability of a success must be the same for all trials, namely P, and my trials must all be independent of one another. If those 4 properties hold, and I'm counting the number of successes out of n trials, I have a binomial random variable, and I can therefore calculate any probability. I know everything there is to know about the behavior of that random variable, right? Which takes us to the Poisson. Now, in the monomial, we count the total number of successes out of n trials. So we know the total number in the set. But what if we have a situation where I don't know the upper limit? Think about the store manager or the owner of a company, of a retail store. I don't want to limit the number of customers that can come into my shop. I'm not going to say they can only be 10 a day. Can't limit that. But I still want to calculate probabilities around the behavior of customers. I'm coming into my shop to maybe ensure that I've got enough people at the tills to serve all the customers coming in. Now, if events occur at a constant rate during any given interval of time or distance, and the occurrences are independent of one another, events occur according to what we call a Poisson process. My random variable x then counts the number of events in an interval with a constant rate of occurrence according to a Poisson process, which means my random variable is a Poisson random variable, and its rate of occurrence, or its parameter that defines it, is this parameter lambda, which is my constant rate of occurrence within that time interval. Possible values of the variable could be anything from 0 to infinity. In theory, I know there's never going to be an infinite number of people in my shop, but in theory, that can happen, right? So if I want to fit this distribution. Again, the probability mass function has been expressed in general terms. So if I can model a random variable using a Poisson, I know everything there is to know about it. I can calculate probabilities around this. And I know what happens on average. What is the expected value, which is just my lambda. Right, that's the Poisson. Taking us to the normal distribution. Now, most numerical variables follow this distribution where the majority of observations are around the center of the distribution. And there's only that one peak with a few observations in the left and a few observations in the right tail area of this distribution, creating this well-known bell-shaped curve. Now, I've said before, real populations are dynamic and it may vary over time, but it may generally follow this bell-shaped curve. So if I can model something with this bell-shaped curve, I actually know quite a lot about that distribution because there are lots of properties around the normal distribution that's really important in statistics. It's also called the Gaussian distribution. It forms the basis of a lot of statistical inference, and it's characterized by 2 and only 2 parameters, which is the mean mu and the variance sigma squared, and it's perfectly symmetrical around the mean. In other words, the size of the area greater than the mean is half the graph, and the size of the area to the left of the mean is the other half of the graph, because it is perfectly symmetrical. Just eliminate these scribbles. Right. Now, let's look at a very unique normal distribution, which is called the standard normal distribution. It's a normal distribution. It is centered around 0, so it's got a mean of 0, and it's got a standard deviation of 1. In other words, a variance of 1, because 1 squared is 1. We typically denote the standard normal random variable with z. It is normal with a mean of 0 and a variance of 1. In theory, it can take on values ranging from minus infinity to plus infinity, and these values are called the z-scores or z-values. We have a set of statistical tables called the z-tables for the standard normal distribution with specific cumulative probabilities for selected z-scores. In other words, it gives areas. So if you look at this picture, and the shaded portion, it's currently attached at some positive number because 0 is in the middle, positive number, and the size of that entire area from that number all the way to minus infinity, that is what's given in this graph. And if I take this number, so this line, and I just move it either left or right, it changes the size of the cumulative area up to that particular point. So the standard normal distribution, the tables are given up to 2 decimal places for those values on the x-axis, the z-scores. And then inside the table, what I call the body of the table, we have the size of this cumulative area up to 4 decimal places. So if my value is 0.23, I will read it as 0.23. That's my second decimal. And where that row, sorry, that's not a very straight line, that row and column intersect. Oh no, lines are not doing what I'm supposed to. We can say the probability that my standard normal distribution is less than 0.23, that specific probability is 0.5910. So it's about 59% of the total graph area. Right. Now, the standard normal distribution is just one of an infinite number of possible normal distributions that could exist. For a random variable x, where x is normal with whatever mean and whatever variance, there are no statistical tables with cumulative probabilities. And it's not mathematically that easy to use the formula that created that density curve to calculate areas under the curve. However, there's a very important and useful property of random variables that states that any normal random variable can be standardized by subtracting its mean and dividing by its standard deviation. And for a normal distribution, this transformation will always yield the standard normal random variable. It's just a transformation. It is like converting rands to dollars or dollars to rands, liters to gallons, miles to kilometers. It's just a link, a transformation where I convert from one unit of measurement to another unit of measurement, but I'm not changing something. If I convert 10 inches into centimeters, that's on a different scale. It's now 25 centimeters, but it doesn't change the distance or the length. It just changed the numerical value. So if I convert from X to Z, it just changes the numerical value, but it doesn't change the other properties and the corresponding areas under the curve. Right, so to calculate probabilities from any normal random variable, what we have to do is we will take the variable, we will subtract the mean mu and divide by the standard deviation sigma, and then I can go straight to the standard normal tables, which is my measurement instrument, and calculate probabilities, provided that the required probability is written in cumulative form. If it is not written in cumulative form, I must just convert it. So if I know how to find the area less than some number, but I'm looking for the area greater than some number, I can just use my complement rule that we saw in probability analysis, because those two events are complements of one another. Right. Now, fitting distributions, this page, I'm going to very briefly talk through this. I don't want to go into details, but this just shows us that probability distributions, I mean, it's not just a theoretical concept. We actually use it. So when we use sample data to estimate the behavior of a population, in other words, we do inference. What we need to know is something about the distribution of our variable of interest. Now, in some cases, we can make an assumption about a variable follows a certain distribution because it reasonably describes it. In other cases, we can actually derive the distribution based on some limit theorems. There's a very well-known one called the central limit theorem that helps us to derive what we call the sampling distribution of the statistic. And then we can use the normal distribution in our inferential procedures. Now, in other situations, we may wish to determine whether an empirical distribution of a certain variable conforms to a known theoretical distribution. There are several methods that we can use to do this, and one of these methods is the chi-squared goodness of fit hypothesis test. So chi-squared is another continuous distribution, one of our known distributions. It creates a certain graph, a certain shape, but that distribution is often used as a hypothesis test for us to determine. For example, let's say I'm a manager at a factory, and I've noted historically, or I believe, that the number of accidents in a month follows a Poisson distribution. from 0 accidents to theoretically infinity, but obviously in reality not. I can then go and test whether the number of accidents in the past month or past few months or whatever the time period would be follows a Poisson distribution by observing how many days on how many accidents were, or rather on how many days I had 0 accidents and 1 accident and 2 accidents, etc., and then compare that specifically of what I've observed to what I would have expected to observe if that was the truth. So it's very useful just to do that comparison. We can also use the chi-square goodness of fit, amongst others, to test for normality. One of the big assumptions in inferential statistics is whether my data are normally distributed. So we test for it. And one way to do it is using the chi-square goodness of fit, where we will divide my distribution into categories and do observe counts, figure out what would I expect to observe if the data were normally distributed, and do a comparison between observed and expected to see if there's sufficient correspondence between those two for me to conclude that the distribution is in fact Poisson or normal or whatever the case may be. Right. So that's how we can fit distributions. That falls more under inferential statistics. So I could touch on that on my next session that I'm going to do. All right. So before I finish off and open the floor for questions, I do have a few applications. I know that in most cases you're not going to do this by hand, but just to show you how to identify things and that we can calculate these probabilities. For example, if I want to calculate, let's rather read this together. The probability that a credit card machine at a store functions properly from historical information is 0.88. Determine the expected number of successful transactions out of a random sample of 4 transactions and calculate the probability that more than 2 of the 4 transactions are successful. In this particular case, if we look at this, we say, oh, we're counting how many successful transactions there are out of 4. That sounds binomial. Well, I've got 4 trials. Each trial is either a success or a failure. It gives a general probability for it being functioning properly. So it looks like the probability of success remains the same for all trials. And we typically, for the binomial, the fourth one about independence is an assumption, but it's a reasonable assumption, is that the success or failure of any of these transactions we're going to assume are independent of one another. So in this particular case, what we have is that I have got a binomial random variable with parameters 4 for n, and my probability of success is 0.88. The expected value of a binomial is just a product of the 2 parameters, so it's 4 times 0.88. So out of 4, I expect 3.52 successful transactions. To calculate the probability that the number of transactions out of 4 exceeds 2, it's more than 2, for a discrete random variable, we will always go to the individual values. We know the binomial can take on values 0, 1, 2, 3, and 4 in this particular case. So all the values greater than 2, that's where the probability that X is either 3 of the transactions or 4 of the transactions. In this particular case, we then just substitute into our known mass function formula, which is n combination X, so it's 4 combination 3, probability of success, so I've got 3 of them, and my failures is only 1, or 4 out of 4 transactions with the probability of success, 4 of them, and the probability of a failure, 0. When we work this out, the probability of this event occurring is 0.927. So as the manager of the store, I'm going to look at this and say, okay, out of 4 transactions, there's a 93% chance of getting at least 2 successful transactions. So it looks like, and if this is still the case, then the machine is still working properly. I don't need to replace it. I don't need to service it. I can make informed decisions based on a conclusion, based on calculations of this nature. Right. Next question is about the Poisson. So at a department store, customers arrive at a rate of 12 per hour according to a Poisson process. Calculate the probability that at least one person arrives at the store in any given 10-minute period. Now, what's important to note with this? Number one, it's given that it's a Poisson process. So we know that the rate of occurrence is constant over my time periods. If I've got 12 people per hour, I can work out how many on average do I have per 10 minutes. So 12 every hour, every 60 minutes. How many every 10 minutes? Well, that gives us 2 on average every 10-minute period because of that Poisson process. What we have here is that I've got a random variable x that follows a Poisson distribution with a rate of 2 per 10 minutes, which is the same as saying 12 per hour. So we have to convert our rate. We are looking for the probability of at least one person arriving in the store in any given 10-minute period. And again, I'm looking for a greater than here. At least one includes one. But because the Poisson distribution has an upper limit of infinity, we're not going to do these individual calculations. We will use the complement rule. This is the probability of 1 minus, or rather, the probability that x is greater or equal to 1 is 1. The complement of this is 1 minus the probability that it is less than 1, which is just the probability that it's equal to 0, because the values of the Poisson random variable is from 0 to infinity. And now I just turn to my mass function, I substitute into that, and that is e to the minus lambda, lambda to the power x over x factorial. Don't worry, this x, the 0 with an exclamation mark, I'm not dividing by 0. That answer is equal to 1. So we're not doing anything wrong mathematically. And the answer to this particular question is 0.865. So if I have customers arriving at the store on average 12 per hour, the chance that at least one customer will come into my store in any given 10-minute period is quite high. So you can't really go walk around. You have to be in the shop. Somebody has to be in the shop to be able to help these customers. Okay. Our last application is a normal distribution. So it is assumed that IQ is normally distributed with a mean of 100 and a standard deviation of 12. Calculate the probability that a randomly selected person has an IQ of at least 110. So for this particular one, I know that my random variable is normal with a mean of 100, a standard deviation of 12, therefore a variance of 12 squared. In order to calculate probabilities, now it looks like all my probabilities are all greater than, but it's just to illustrate a point in terms of using my cumulative areas. The probability of IQ at least 110. In terms of calculating probabilities from a normal distribution, the first thing we're going to do is to standardize, because I want to use my standardized instrument, the standard normal tables, to be able to calculate this probability. When I standardize any normal random variable, I will get the standard normal random variable. And how do we standardize? We take the value, we subtract the mean, and we divide by the standard deviation. So I have got the probability that the standard normal is greater or equal to 0.83. The problem with this is that my cumulative tables are in this format, less or equal to some number, which is not what I'm looking for here. So in this scenario, I have to use the complement rule. I'll pause for a moment. Look at my notation for the standard normal. It says less or equal to. Now I've got notation equal to. In the continuous context, that doesn't matter. That is irrelevant. That equal sign in my inequality is only important when I work specifically with a discrete random variable. For a continuous random variable, that is irrelevant. Less than, less or equal to, same thing. I will now go to my tables to find this particular probability, z less than, or less or equal to, if you like, 0.83. So it's 0.83, and the answer is here. And I get a total final answer 0.2033. So in this particular case, in this population, if that is the distribution of IQ, then the probability, then about 20% of this population have an IQ of at least 110. Okay. And that brings me to the end of the presentation and the training session. So thank you very much, everybody. I'm going to stop sharing and we can open the floor for any questions or comments.
Thank you so much, Ms. Smith, for the very insightful and engaging statistical analysis workshop. Your clear explanations and practical examples and your patient guidance with, this complex statistical analysis concepts was really easier to understand. And I think most of the attendees here can attest to that. We truly appreciate your effort, for tailoring this session to everybody's needs and also encouraging the active participation. So in this regard, we can open the session to questions. I see we have a hand up there by Dr. Gabriel. Dr. Gabriel, you can unmute your mic and speak. If there's any other questions from the participants, please kindly type them in the chat box, or you can raise your hand and you can you can contribute. Thank you so much.
Thank you, Lawrence. Can you hear me?
Yes. Hello, Gabriel.
Thank you so much, Ms. Smith, for agreeing to facilitate this session. I think you just took us back to the time when I was doing econometrics and applied statistics, during the undergraduate studies. I'd forgotten much of these things. And I still have to go back because I couldn't really, because of other obligations, I couldn't really follow every step of the way. But I think this is a very, very important reminder. I will maybe, because we do also upload the resources on our Moodle communities after the session, I will have to revisit and just attentively follow every step of the presentation from when you began until this point. But thank you so much for this. It's a very, very important insights, that took us back into some of the concepts that we knew of, but now yet totally forgotten. Thank you so much.
You're welcome.
All right.
Okay, Gabriel, I thank you for those kind words. And you know what? As I said, that a lot of this, you're not going to take pen to paper and calculate these probabilities and use those rules. But what is quite interesting when you start doing research, and specifically because a lot of this actually feeds into when we go into inferential statistics, just to understand a little bit more about probability and the concept, it helps you to have this foundation. So it really just gives that foundation. So I hope that, yes, it's a refresher.
Yes, yeah. Okay, thank you so much.
You're very welcome.
Guys, there any other questions from the participants? Let's see, there is no questions in the chat box. There is no hand raised. I believe the session was very, very clear there. Your presentation was very clear there, Ms. Smith. I see there's no questions for you.
Okay.
I see the practical examples that in the applications that you provided, I think they came in handy and were much easier to follow. So,
and I'm going to this presentation that I've done. Let me just make 100% sure it should be still with all my scribbles in it. I hope so. Well, if it isn't, no, it is not. So I can just add those questions. As I've worked it out, it was supposed to keep it. I'll check it out. Then all my handwritten, I know it's not the best handwriting in the world, but it can save that, and I can save that as a PDF so that you actually have those examples. You can send it to all the people that attended.
Yeah, definitely.
Okay.
So in this regard, you see there's no questions. So I believe all the participants, we are clear there. I believe we have no questions at all.
Well, then.
Or if you are shy, you can type it in the chat box, or if you'd like to make any contribution, Oh,
Yes,
you can, yeah. And just a reminder that I've posted the feedback survey in the chat session for all the participants. Please kindly fill that in. And also, you can also provide some kind words to our facilitator there for this session. If it was clear for you and everything worked well, and you can see she provided real-time examples there. So please kindly just fill in the feedback survey. And also this will ensure that you get a certificate of attendance for this particular workshop.
Yes,
So
can
in
I
that
also just quickly ask on that feedback, Lawrence? I just want to ask all the participants here. I think what might be useful is, well, it's a very simple, informal thing, if you like. It's a stop, start, continue. If you want to tell me what we shouldn't be doing in a session like this, particularly because you have your specific research requirement. So I think it might be useful to just get some feedback, whether, what else in a session like this would you have liked to see? Maybe what was too much, what was not enough, or what was okay?
Yeah,
Because
definitely.
that would be
Certainly.
very useful going forward to see the feasibility of doing something. I still think it is important just to refresh, just to get that baseline. The more important for your research when you do your own research, of course, is to understand descriptive statistics, inferential statistics, and how to do that, and what is a p-value and how do we interpret that. Of course, that's not what you get from today's session, but it would be very useful to know if this was helpful. So, Gabriel, thank you for your feedback anyway so far. So that would be, I think, very important. So please, I would appreciate that.
Yes, certainly. Just a question from my side. I just want to ask, how do you recommend that we continue building our skills in statistical analysis?
Okay. Well, can I just ask, are you talking in general for yourself or
Yes, in
like
general
for
for
new
myself.
researchers in general for yourself?
Yes, myself, yes, and research, yeah.
I think that there are different routes to go here. I mean, we're not trying to make statisticians out of everybody. Not everybody can be a statistician. So
Yes,
that's
true.
where there are some statisticians that are available, like at StatCon or some other freelance statisticians that do some analyses. I think what's very useful is if people do have more insight in what it means. To build your own skills, I think is just by starting when you do research and working with somebody like people at StatCon or some statistician and just absorb and observe and perhaps even a few extra training courses or short courses, short learning programs that are available that might help, and just keep doing it, because statistical analysis is, you can sit in a classroom and dream about doing statistical analysis and learn all the theory around it, but there's actually an art to it, to do statistical analysis, to really understand your data, being able to look at it and interrogate it and get out of it and understand it takes practice, sitting with it and working with it. So I think work with a statistician. If you've already done that, keep doing that and start doing it on your own and talk to the statistician and get insight, have discussions. That's the best way to learn. When I worked in market research, I was the statistician, and there were a lot of research psychologists that worked in market research. And it was so nice to work with people. They didn't have to do the statistical analysis. But what really helped was that there was an insight and understanding. So when I talk about certain techniques or p-values and hypothesis testing and confidence interval estimates, there was more of an understanding. And I think that's what's important. Yes, you're going to do your own statistical analysis, but it doesn't mean you have to become this big statistician. It really helps when you have that insight and understanding. Yes, Gabriel.
Thank you so much.
I just wanted also to compliment what you are saying in answering Lawrence, that this is it's a sort of a basic foundation for quantitative analysis. So you should be sort of in possession of these and accustomed to these concepts. If you are to sort of be able to analyze quantitative data as well as presenting it. So it's very important for quantitative research designs, including the presentation and analysis of quantitative data. So if you don't know probabilities, you are also unable to test hypotheses, make inferences and so on that you can obtain from statistical analysis.
Thank you. Thank you so much there, Ms. Smith and Dr. Gabriel, for clarifying on that question. Very helpful on that. I think it's just about, just going on and revisiting this, and also, as you say, just about practice. And I think,
Yeah.
Going forward, you definitely be able to build the skills in such statistical analysis concepts. Yeah, definitely. Thank you so much. Yeah, thank you so much.
Absolutely.
Yeah. In that regard, I see there isn't any further questions from the participants. There is no hand raised. And as I have indicated that I have posted the feedback survey, and as Ms. Smith indicated that please just write what are things that can be improved, or what are some of the things that you think she might have missed, or maybe that needs further clarification. Then I'm sure she can incorporate them, as she will be also facilitating further session on statistical analysis. So in that regard, if there is no further questions from the participants and no hand raised, is there anything else that you'd like to add before we can end this session, Ms. Smith?
From my side, no. I just want to say thank you to everybody for showing up and for giving me this opportunity to teach this. I love statistics and I love teaching, so it's been fun. It's been interesting. So
Yeah, definitely. Looking forward to seeing you on the next one. Definitely. Absolutely. Thank you so much. Dr. Gabriel, you want to say something?
Yeah. Lawrence, I wanted to ask that, are there other sessions that are coming after this one that Ms. Smith will be presenting?
Yes, there's one that is be coming up, yes.
Yes, no, two actually. So I'm doing inferential statistics tomorrow. Okay. And then the day after, on Thursday, I'm doing a session on very basic statistical analysis in Excel, just graphical representation and statistical analysis in Excel. It's not the best tool. There are better tools, but what if that's the only thing you have? Jeez. So we'll be looking at that. So there are two sessions still to come.
Yes, so sure they continue to build on what you have done today, isn't it?
Yeah, so what's going to happen tomorrow in inferential statistics? I am going to start off by talking about this sampling distribution that I spoke about of the mean, so we can do inferential statistics. Then I'll cover quite a few hypothesis tests, and then also looking at regression analysis and correlation. But I'll give you the theory and everything behind it, but then we'll look at it output based. What does it actually mean? And part of my discussion tomorrow will also include what on earth is a p-value. So really understanding p-values.
I think I will be part of that session as well tomorrow.
Definitely. In that regard, thank you so much, Ms. Smith. Hoping to see you tomorrow, and to the participants also hoping to see you tomorrow. We have the session tomorrow from 10 to 12, statistical analysis, inferential statistics, and regression analysis. So hoping to see everybody there, just to carry on from where we left off today. In that regard, thank you so much to you, Ms. Smith, and to all the participants for joining this session. In that regard, have a great day further. I'll now be ending the session. And thank you so much, and enjoy the rest of your day.
Thank you, Lawrence. Thank you, everybody. You all take care. Bye.
Thank you. Bye.